And so the mole is, chemical quantities are going to be anything that are related to reactions, things like energy, moles, conservation of mass. These are the chemical quantities that we're going to be talking about. The mole is something that people usually, when they've done at least one course in chemistry, they hear about and they think of it as this kind of complex idea, like what does that mean? What is the mole? What are we talking about? But a mole is really just a counting device, right? And so because atoms are so small, right, that means that dealing with the number of atoms involved in a single reaction for something like a cup of water involves something like trillions of trillions of trillions of trillions of atoms, right? Like something to the power of 12, to the power of 9, to the power of 2, for example, is the number of atoms in a single cup of water. And so the way to simplify these types of relationships or determine the amount of the things that are involved in chemical reactions or physical processes or chemical processes is to use a counting device. And all a counting device is something that we use to represent a certain number of things, right? So a mole is like the same thing as saying, oh, I have a dozen of this, right? What is a dozen? 12, right? But it could be a dozen of anything, right? You can have a dozen bats, a dozen lemons, a dozen cars. That just means you have 12 of that thing. A mole is the exact same idea, except we're dealing with a very large number of things because things in chemistry are inherently very, very small. And how do we define a mole? Well, a mole is not a dozen things or 12 things. A mole is 6.023 times 10 to the 23 things. Right? So that's about 10 million cubed things that we're talking about. And that's just one mole. Right? In this room, we may have 100 moles of gas in here, for example. And so this is just a counting device, and it's represented by Avogadro's number. So Avogadro's number is the chemist who was thinking about a lot of these things back in the 1600s or so. And Avogadro's number is 6.023 times 10, 6.022 times 10 to the 23 things per mole. All right, what do I mean by things? Well, that can be anything that we're looking at. Right? We can have a mole of students. That means there would be 6.02 times 10 to the 23 of you. A mole of planets, which would be probably all the planets in the observable universe. A mole of solar systems, which would be more than the observable universe's solar systems that exist. And we use this in units like this because you can use them in unit conversions. Right? If we want to know the number of things that are present, given we have the number of moles, then we can use that to convert between the two. Right? So this is just a counting device. It's not some scary concept. It's just a counting device that represents a very large number of things. And so if we have a mole of hydrogen atoms, how many actual hydrogen atoms do we have? 6.02 times 10 to the 23 hydrogen atoms. If we have a mole of hydrogen gas molecules, how many gas molecules do we have? 6.02 times 10 to the 23 H2 molecules. If we have a mole of water molecules, how many water molecules do we have? 0.22 times 10 to the 23 water molecules. So as you see, it's easier to deal with 1 mole of it rather than writing 6.022 times 10 to the 23 of those things every single time. Right? We're saying that 1 mole of H atoms is the same thing as saying 6.022 times 10 to the 23 atoms.
What was the actual number you said?
That is the actual number.
No, we were to calculate it's like 10.
This is, like 10 to the 23 is like 10 to the 7 to the third power, right? If you were to do rules of exponents, 10 to the 7, which is like 10 million to the third power. So it's like 10 million cubed is how you get there. That's how you get a rough estimate for how much stuff it is. Really, if you were to write this down, it would be 6.022 with 23, or I guess you have 20 zeros after that. So a very, very long number, an annoying number to write. Which means that if we're doing calculations with these things, probably what type of notation will be useful to do these calculations? Scientific notation, right? Because if we're plugging all these exponents into our calculator, that can make things kind of nasty pretty quick. All right, so it's easier to deal with a mole than it is to deal with this number every single time. And so what people have done is they've measured the mass of single atoms in relation to a mole of that substance. So the mole, Avogadro's number, gives us a relationship between the moles of something and the actual number of those things. And what our periodic table, or what scientists have basically calibrated mass to, is the mass of a substance and 1 mole of that substance. So when you look at the periodic table, you see that the mass, the number under hydrogen is the atomic mass number. That's 1.01 AMU is what we say. What that number represents is the mass in grams of 1 mole of that substance. Right? Because it's easier to say, oh, we have 1 gram is equal to 1 mole of hydrogen than it is to say 1 gram is equal to 6.0 times 2 to 6.022 times 10 to the 23 atoms of hydrogen. All right, so this gives us a relationship between the moles of a substance and the mass of a substance. And how AMU, which is the number, right? This is what the A number was when we were looking at protons, neutrons, and electrons, right? That's why we actually have decimal places here, right? Where it's not whole numbers like when we were dealing with finding the number of neutrons, protons, is because these numbers actually represent the actual mass of these atoms. And not just these atoms, but the mole of, 1 mole of these atoms. And so an AMU is defined as a gram per mole. And so what the mass of 1 hydrogen atom is 1.008 atomic mass units. What that means is that the mass of 1 mole of hydrogen atoms is equal to 1.008 grams. And so if we look at these equalities here and we think about conversions, what does this look like here? If we go all the way back to our unit conversion days. All right, we had conversion factors, conversion equalities. Could we classify these as any of those? We classify these as conversion equalities, right? Because we're saying we have a conversion between 1 mole of H atoms to the grams of H atoms. So for each of these conversion equalities, we get how many conversion factors? 2, right? So we have 1.008 grams per mole H and 1 mole per 1.008 grams of H, right? These are 2 conversion factors from our conversion equality. And where do we get that number from? Well, that number is given to us on the periodic table. And what do we call that number? Well, we're going to call that number the molar mass. Why? Because it's the mass of 1 mole of substance. All right, so we call this the molar mass, and I usually abbreviate it just as MM. And the molar mass is given to us by the periodic table, right? So if we have our periodic table, we have our element, our atomic number, and the molar mass is given right below it. Which means that 1 mole of X is equal to the molar mass grams of X, if this is our random element here. Which means the molar mass per mole, or 1 mole per the molar mass in grams. And this is how we go between the moles in grams of a substance, right? So without really having, gone into too much detail, we've already come up with a way that we can go from the mass you measure in the lab to the number of molecules that are present in that sample. Just from these two ideas, the idea of the mole and the idea of the molar mass. And so for a single atom, it's what's given to you on the periodic table, right? Here, if we're looking at the molecule, H2O, how do you think we'll find the molar mass of the entire molecule?
Multiply the mass of hydrogen by 2.
Yeah, you just add up all the masses of all the atoms within the molecule, right? And we have how many hydrogens? 2 hydrogens. And how many oxygens? 1 oxygen, right? Which means that the molar mass for 2 hydrogens is 2 times, what's the molar mass of hydrogen? 1.008 grams per mole. And especially with unit conversions, it's important we always include our units, right? So I know the last chapter, or last couple chapters, we haven't had to worry about units too much. When we're doing these conversions, units are the most important thing, because that's exactly how we know where we're going to end up, right? And this is H2O. And then what's the molar mass for oxygen? It should be 16, right? 16.00. It depends on what periodic table, grams per mole. And so if we add those up, 2 times 1.008, this will give us the molar mass of water is going to be 18.016 grams per mole H2O. That's how we would solve for the molar mass of a molecule. All we're doing is we're adding up the molar masses of all the atoms within the molecule. Right? It's like if you had a bag with certain contents in it, you want to find the total mass of the bag. One way you can do that is just by measuring the mass of everything that's in the bag. The bag is our molecule, and the atoms are what's inside the bag, and they comprise the molecule. And so it's important to be able to look at the chemical formula, right? So we have to understand how the chemical formula works, which we talked about a lot with ionic and covalent naming and determining the chemical formula, to be able to determine the molar mass. Why? Because you need to know exactly how many atoms are in each molecule. Right, so here we have another example. We have calcium hydroxide, right? This is an ionic compound. Hydroxide is a polyatomic ion. And we want to find the mass of 1 mole, meaning that we just need to find the molar mass of this molecule. And so how do we do that? We need to add up the molar mass of what atoms? add molar mass of calcium.
Oxygen and
Ha- yeah, oxygen and hydrogen. How many oxygens?
one.
2, right? Because we have, in our chemical formula, the parentheses means that we have 2 of everything inside that parentheses, right? The subscript outside. This means we have 2 H's and 2 oxygens. Right? Because of the parentheses there, it means it multiplies everything inside by 2. So we have the molar mass of 2 oxygens plus the molar mass of 2 hydrogens. And so what's the molar mass of calcium? 40.07 grams per mole plus 2 times 16.00 grams per mole plus 2 times 1.008 grams per mole. Adding all these together, we get 40.07 plus 2 times 16.00 plus 2 times 1.008. I actually added a negative sign. Plus 2 times 16.00 plus 2 times 1.008. We should get 74.09 grams per mole calcium. All right, this is our molar mass of the molecule itself. Is anyone confused on how we get these numbers, where they come from, or the idea? Vanessa?
It's actually not, like, for the answers, do we have to write the whole entire formula, or do we just do, like, CA? Because, like, right now in the answer, you can just put, like, the mole.
Oh yeah, that's you're right. That's a good point. It should be CaOH2, right? Because this is the grams of calcium hydroxide, not the grams of calcium per 1 mole, right? We're looking at the grams of 1 mole of this molecule, not the grams of 1 mole of calcium. Yeah, I just forgot to write it. It's good to clarify. All right, thumbs up, thumbs to the side, thumbs down on this idea. Because if everyone's thumbs up, then I'm gonna move to then using this for unit conversions, right? So the next 2 slides are a couple of practice examples, which you should go through, right? So salicylic acid, which is just aspirin, you have now 7 carbons, 6 hydrogens, and 3 oxygens, right? So that's a little tedious to do, but you can calculate the molar mass of that on your own. And so this, everything we've talked up to this point, chemical quantities, gives us a conversion between the mass of a substance, the moles of a substance, and the number of particles of a substance. Right? So how do we go from the mass of a substance to the moles of a substance? What do we use, right? We have 2 conversion factors we've talked about, Avogadro's number and molar mass. Which one do we use to go between mass and moles? Molar mass, right? We use the molar mass to go between these 2. Once you have the moles, and we want to find the number of things that we have, what do you use to go between those 2? Avogadro's number, which is N sub A. And let's talk about how we use those numbers to go between them. If we start off, right, mass is in units of grams, moles is in units of moles, and number is in, we're going to put units of things for both of these. If we start off with something of grams, how are we going to use the molar mass to end up with moles of that substance? Right, because there's two ways we can use the molar mass. We can multiply by the molar mass, or we can divide by the molar mass. Right, if we're going from grams to moles, we should end up with units of what? Moles, right? And if the units of molar mass, remember this bracket here I'm using, it means units, is grams per moles. If we went moles in the numerator, how should we use the molar mass? What are the units of 1 over the molar mass? If you invert it, what does it do to that ratio? It flips it over, right? So that'll be moles per gram. Right, so if we're going from grams, meaning we start with something in units of grams, do we multiply by the molar mass or by 1 over the molar mass? 1 over the molar mass. How do you know? Because 1 over the molar mass is equal to moles over units grams. We have moles in the numerator there, which is where we want it if we want to end with units of moles. So this is going to be 1 over the molar mass is how we get in this direction. If we go from moles to grams, that means we want grams in the numerator. We should use what? Should we multiply or divide by the molar mass? We should multiply. We just multiply by the molar mass. And what about Avogadro's number? What were the units for Avogadro's number? Things per mole, right? And so what are the units of 1 over Avogadro's number? Moles over things. And so if I start with units of moles, and I want to go to units of things, or number of things, what should I do? Multiply or divide by Avogadro's number? What do I want in the numerator? Multiply, because we want things in the numerator, which is when we multiply just by Avogadro's number. And what about when we go in the other direction? What do? You divide. 1 over NA. So all I'm doing here is I'm giving you a little flow chart of how you go between these substances without having to look at it as a unit or conversion equality right away. It's exactly what we did before. It's just I'm giving you the ratio and what you actually do with the number itself. The molar mass depends on what chemical or atom you're looking at. Avogadro's number is always going to be the same number. And when I say that, I'll make a slide after this one just to kind of illustrate a little bit better what I just said in words, why this is just the same thing as looking at conversion factors and conversion equalities. Am I good to go on to the next? Anyone still writing? All right, so if we have 1 mole equals the molar mass of grams, right? That's what the molar mass says, is 1 mole of this substance equals this many grams. That means that our two conversion factors are 1 mole over 1 molar mass, or whatever the number of molar masses, of grams, and molar mass grams over 1 mole. This is the same thing as me just writing multiplying by the molar mass. And this is the same thing as multiplying by 1 over the molar mass, or dividing by the molar mass. Avogadro's number says that we have 1 mole equals Avogadro's number of things. So if we do the same thing, we get 1 mole over Avogadro's number, and then Avogadro's number things over 1 mole. Right? This is the same thing as multiplying by Avogadro's number, and this is the same thing as dividing by Avogadro's number. Right? So here we have it more explicitly written out in terms of the conversion factors. But what does this mean when we actually are doing this or plugging this into our calculator? Well, if we want to go from grams to moles, we divide by the molar mass to give us that. Why? Because that's the same thing as multiplying it by this conversion factor, which is just 1 over the number you calculate from the periodic table. All right, so this is equivalent to the previous page. Any questions on that? So I know sometimes it's hard to see it in these ways, so I'm trying to explain it a couple different ways, and hopefully one of them sticks. Right, but this idea is pretty important for, you know, the rest of the course. That's why I'm trying to spend some time on this. All right, so let's apply it then. Right, how many moles of iron are present in 25 grams of iron? Right, so the chemical formula for iron is just Fe. It's just a single molecule. And you're given the mass that you have, right? So you're starting from what value, and you want to convert it to what? You want to go from grams to moles, because it's asking you how many moles of iron do you have. And how do you go from grams to moles? What are you going to use?
1 over molar mass.
Yeah, you're going to use 1 over the molar mass. You're going to multiply by 1 over the molar mass. And so what is the molar mass of iron? .85. And what are the units of the molar mass? Grams per mole of iron, right? Grams of iron per moles of iron. And so how many grams am I starting from? 25.0 grams. I'm going to multiply it by 1 over the molar mass, which is 55.85 grams of iron per 1 mole of iron. What happens to my units of grams here? They cancel out. And I'm just left with moles of iron, which is what I want. And so, where'd I put my phone? 25 divided by 55.85. That was multiplied 25 divided by 55.85. This will be about 0.4. We're given 3 sig figs, so we end with 3 sig figs for 8 grams of iron. Right, so all we did is we divided by the molar mass, right, multiplied by 1 over it. In terms of a unit conversion, it's useful to write it this way. Why is it useful to write it this way? Can anyone see the use in that? Abe?
Easy to cancel out things.
It's easy to see how the units cancel out this way, right? Numerator, denominator cancels out. That's why it's easier to write it out as a unit conversion. Mathematically, what did we do though? We just divided by the molar mass. mass to give us that. Because 1 over, if we were to do 25.0 grams Fe divided by 55.85 grams per mole, right? This is the equivalent, it's the same thing. Units of grams cancel out here. And we're left with units of 1 over mole, which is just units of moles, right? So we can do it this way if it makes sense to us. But I feel like it's easier to see that the units cancel out this way in our conversion factor.
Wouldn't the final answer be moles instead of
Yes.
Okay. Just wanted to be sure.
No, yeah, this is very good to be sure of that. Thank you. Moles of Fe. All right. How do you guys feel about this example? This is a one-step conversion. Thumbs up, side, down. Okay. Let's see. Mass. What if we have a certain mass of magnesium and we want to find how many atoms are present, right? So what do you guys think the conversions are? Where are we starting from? Where are we going to start from? What number? We should be starting from 5.00 grams. And what do we want to end with? Atoms, right? The number of atoms. And so what conversions do you think we need to do to get to there? Right, do we have something that goes directly from grams to number of things? Avogadro's number gives us the relationship between number of things and what? Moles, right? And we're given mass. So do we have something that gives us something between mass and moles? The molar mass. And then once we're in moles, we can use Avogadro's number to go to the number of things. So we're going to go to moles, and then we're going to go to the number of atoms. We use 1 over the molar mass to go to the number of moles. And to end with the number of things, we use Avogadro's number. All right, so this is our flow chart for how we're going to get to the units that we want. Right, because we're starting from mass and we end with the number of things, we first have to go to moles and then use Avogadro's number to go to the number of things. And what we find is, especially when in lab we're going to talk about chemical reactions, is that going between some mass number into moles is what allows us to the universe of the moles is what allows us to go from products to reactants, from numbers of things to other numbers of things, and vice versa. Right, so converting things into moles makes things a lot simpler. All right, so we're going to end here for